But today I'm going to talk about adaptive subgroup selection in sequential trials. This is a very interesting piece of work for me because of the fact that it really shows the power of R, and I think it's perfect that I can actually present it at the useR conference. So what's the idea here? The idea here is that when you're comparing an existing treatment against a new one, for example, and you're designing a trial for testing a new intervention, almost always the trial designers have, yes, can't hear? Maybe I should be here. How about that? Okay. So the trial designers, just generally cannot forecast, what the sources and the of heterogeneity that can be in patients that actually are enrolled in the trial, and also the magnitudes of the treatment effect, for example. And so if you ignore these characteristics, then you may actually have a false negative result because you've just wasted your money. And if you actually restrict patients and try to have a very tight trial, then of course you get in trouble with the company sponsoring the trial because of the fact that they would like to have the drugs sort of be useful for a wide variety of patients. And so it also leads to recruitment problems because you have a very strict criterion for recruitment for the trial. And any person who's designed a trial knows that that is a big concern. And so today I'm going to talk a little bit about an adaptive choice of patient subgroup that lets you, have a natural compromise between ignoring this patient heterogeneity as well as using this inclusion-exclusion criteria. So I want to just quickly mention my collaborators here. Lai is my colleague in the Department of Statistics. Phil Lavori is a colleague in the Department of Biomedical Data Sciences. Olivia Liao was a graduate student of C, but now she's at Uber. And Kai Wai Sang is now a professor at Hong Kong. And Martin is the only doctor in the group. So, and I'll begin with a motivating trial here. So the idea here is to compare standard medical therapy with an endovascular procedure to remove clot in people who have ischemic strokes. And of course, those are one of the key predictors of how well you do after stroke is the fact that how soon are you treated, or how soon is a stroke discovered, and an intervention is done. And so there are two characteristics that kind of tell you how well you're going to do if one is this diffusion weighted imaging, which is actually a measure of the size of the central infract that is not considered salvageable. And so which means that the reperfusion that people perform to actually maybe make the tissue come alive is that process is affected by how large this area is. And then also there's this time since stroke, which is the longer you wait, well, your prognosis is going to be worse. And so here are two baseline characteristics that you may want to somehow consider in your, you may, for example, think that people who have you may have an intervention that says that if you have somebody who's only had a stroke, say, the last 20 minutes, maybe that person actually has a better outcome with your treatment. So that's the kind of trial that's motivating this work. So the clinical outcome here is the change since baseline of an ordered score. This is a score that people use. It's called a Rankin score. It sort of measures the change in impairment, and it's a number that goes from 0 to 6. And then the clinical hypothesis that we're looking for is that in some subgroup of patients defined by this Cartesian product, dWi by TSS, and I'll tell you how we construct that, the null hypothesis of no treatment versus some effect is false. And so what we would like to do is to sort of find the largest subgroup where this actually happens while controlling type 1 error. So here's a simple partition. In fact, this is the one that we used. So you have two dWi levels, low and high, and then you have the time since stroke, which is actually characterized by three time intervals, let's say short, medium, and long. And we are going to call these categories C1, C2, C3, C4, C5, C6. And we're also going to sort of denote the prevalence by these PIs. And based on some a priori evidence, well, this is where the doctor has to help you, by the way. This is not something a statistician can tell you. What we're going to do is that we're going to actually order these cells by decreasing chance of a beneficial effect. So for example, here is a group that pi1 is a group probably that has the best chance, okay? So for example, if you have a short low DWI and a short time to stroke, maybe you're going to do best. And here, maybe you're going to do the worst. And so you construct these nested groups. And now, of course, the goal is to see, okay, first off, you would like to be able to test whether the intervention works in the largest subgroup. If it doesn't, can you find a smaller subgroup where it actually, can you do a hypothesis test where in a smaller subgroup where it may be beneficial? So I hope the problem is clear. Okay, so I think that I'm just going to use some notation. I had a bit of math before, but I think I took it all out just curiously before this talk. So I will just say that, again, you know, it's standard. We're going to use standard normal theory here. So we have a mean effect, and we are testing, for example, so this capital J, which will play a role, is capital J is a number of groups. So J is 6 in this case. So you can actually use J equals 6. And what we're going to do is we're going to test these hypotheses that the treatment is not effective versus where a group that it might be effective. And again, we don't have information from previous studies about this effect sizes. So one way to approach this is to say, ask the doctor, what is the largest, I mean, this question is something they can answer. What is the largest study you could do? And usually they can give you a number, and from that you can infer back to something called the implied effect size for a particular alpha and a beta, right? So you can work backwards that way. So I think that what we're going to do is we're going to use that to sort of determine the overall sample size. And then what we're going to do is first we're going to test in the largest subgroup. So we're going to test H capital J, which is H6 here, right? And if that is not rejected, then what we will do is that we are able to pick a subgroup among the remaining 5. And then that can be tested. And you can do this without loss of, bleeding type 1 error. And so that's really the innovation here. So I'll tell you a little bit about the test statistics and sequential testing here. So again, we're going to use multivariate normal setting. So which means that, you know, the ZIs are all jointly multivariate normal. So that means we know the theory pretty well. And we're also going to use sequential testing, so which means we're going to have testing for both efficacy and futility. So there's a paper by Lai and Bartroff that pretty much says that you can get optimal tests with just 3 stages. So we're going to use a 3-stage test. And the total sample sizes, so remember the doctor specified N3, which is the maximal sample size, right? So what I'm going to do is these NIs are cumulative. So what I'm going to say is I'm going to partition, say, I'm going to recruit N1 patients for my first stage, then N2 for my second stage, and N3 is the final third stage, of course. And the nice thing about this normal setting is the fact that you can actually write down some of the covariances and so on to be able to compute some probabilities. And so, for example, here is the interstage covariance for group J. So in other words, the group J is fixed. So J is 6. Again, you can use that as throughout. If you capital J is 6. And what I can do is, if L and L prime are 2 different stages, I can actually write down the covariance between these test statistics. And it has a nice form. And it has a form that's almost, if you assume equal randomization, then it turns out to be just the square root of the ratio of the sample size. Okay, and then what about covariance between groups at a fixed stage? Again, that turns out to have another nice formulation here, so which is it's just square root of qi over qj over qj prime, where these qj's are the cumulative prevalences of these groups. So that's about the math I will use, okay? I won't tell you any more because the rest of the stuff is some detail. I should also mention a practical note here. The Rankin score is, of course, discrete. So in our implementation, we actually use the Wilcoxon form. And again, what we have to do is we have to standardize a Wilcoxon form, and that you can do again very, very easily. That's not a problem. So here is the final procedure. And I'm going to take a little bit of time to actually go over this. So what we do is first I start accruing patients in the largest subgroup, so capital J. So I'm going to accrue patients in all 6 subgroups. At the first interim analysis, what I'm going to do is I'm going to test H6, which is effect in the largest group. Now, if I have efficacy, I stop. I've got the largest group I want. If it is futile, what I do is I select a subgroup I had. So the way I do this is I choose the largest, simply put, I'll choose the largest Wilcoxon statistic among the remaining groups. And that's my group I had. And then I test that subgroup. If I have efficacy, I stop. Again, if I have futility, I stop. Otherwise, and here's the key part, I only accrue in that subgroup from now on. So once you choose a subgroup, you drop the other groups and you only accrue from now on. So which means that you can lose patients, right? And so even though the maximal size that the doctor specified was some number, well, we are not really sticking to it because you're going to be trying to get to the N2 and so on, so you're actually over-recruiting. And that's the fix that the actual implementation of the diffuse trial makes, and I'll mention that again. And so if you follow this throughout, the same procedure holds for the second interim analysis and the third interim analysis and so on. And I'm going to skip in the interest of time how we calculate the type 1 and type 2 error, but suffice it to say that the critical values, there are critical values that you need to compute, and this is where, again, things in R we can use nicely, which is we use a technique called recursive numerical integration to actually compute these quantities B, C, and B tilde. So the B is the critical value for rejection in stages 1 and 2, and in stage 3 it'll be another value called C. And this B tilde is a value that is the futility boundary, and that's only computed at stages 1 and 2. And I'm just going to quickly sort of, Sebastian said that, he couldn't fit, the code was pretty long for him to show because it was too complicated. This is complicated too. So what I did is I just took some snapshots of how one would specify the design parameters, for example. This is all part of the vignettes in the package that you can download. So here is a equal prevalences in 6 groups, and I have the null and alternatives. And at the bottom, for example, I have the type 1 error that I've set for this design, and type 2 error, and also the epsilon, so which is a sort of a compromise between how much I want to spend in the interim analysis and so on. And I can compute the B tildes. And if you look how this design behaves, you see that it's a little conservative. So for example, I had asked for 0.05, I really get something like 0.037, but it certainly does control the type 1 error. And in the interim part, it actually does pretty well. The slight fix for the diffuse is the fact that I told you we lose patients, so there is a way to sort of estimate these patients, how much loss you will be, and account for that. And that's what the diffuse trial does. And this is a trial that's actually now in progress at the NIH. And this one, again, you'll see that it's a similar trial, but again here, I use a 0.025 as alpha, and I, again, control the overall error, but there is a slight bleeding of the interim, error control. And this is because of the fact that now the number of patients that you lose is a random number. So actually, you can use simulation to fix this. It's not too hard to fix it. So the package assistant does this, and it's on CRAN. It's been on CRAN for a while. You can download. It lets you construct designs, provides functions to explore characteristics, etc. But I think my summary here is the following, and maybe I can make this comment overall. So R really is focused to help in this regard because every time I look at a trial design and I go and try to implement it, it's written in some obscure journal, and actually recoding that procedure is nightmare, number one. So the second thing is also deploying the procedures, and even more of a nightmare. And I think this package was developed, and we're going to have soon a paper when the trial ends, that shows that you can develop these open sources package in R, And then you can use a system like OpenCPU to deploy these in existing environments without asking them to change anything by means of RESTful APIs. And so more is forthcoming, but if you want to look at the latest and greatest version, you can look at the GitHub site. Thank you.